Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to be reviewing cyclohexane, and in particular, the chair, the boat, and ring flipping, as well as how to convert between the two-dimensional and the three-dimensional representations of the molecule. Let's start with the basics. On the left, I have a flat representation of cyclohexane. There's an issue with the flat structure. It does not represent how cyclohexane actually looks in three dimensions, like we have on the right. Each carbon in cyclohexane is supposed to be tetrahedral, and tetrahedral centers have an ideal bond angle of 109.5 degrees. So what the carbons do is they have to rearrange themselves in this chair shape that we have on the right. I do have a ball and stick molecular model of these images, and you can see when I take a picture from the top view, you can see that it looks a lot like that flat representation that's drawn above it. But when we actually view it from the side, you can actually start to see that three-dimensional shape, which looks a lot more like that chair drawing in the top right. On these structures on the bottom left, I have added two methyl groups to each of the carbons in the cyclohexane molecule. Normally, textbooks will just draw in the hydrogens. However, I think hydrogens get in the way when drawing this because you actually need to write H in each of the positions. So I just chose to use methyl groups because I can just draw a single line to represent them. Anyway, these two structures show a flat and chair representation of the same cyclohexane molecule substituted at each position with those two methyl groups. It is much easier to visualize the tetrahedral molecular geometry of each of those carbons in the cyclohexane when viewing the chair form. Let's talk a little bit more about the chair representation of cyclohexane. If you have a professor who actually spent the time to go over in detail how cyclohexane looks, this might seem very obvious to you. However, from my experience, a lot of students never actually quite understand what the chair form looks like. So in the three-dimensional drawing, or this chair, it is much easier to see that three of its carbons are positioned above its other three carbons. We call these carbons up carbons, and we call the carbons between them down carbons. Just so there is absolutely no confusion on this at all, I'm going to go ahead and circle the three up carbons in red. The three carbons that are not circled are the down carbons. Now, if we use a molecular modeling kit and actually build cyclohexane and view this molecule from the side, you can actually see that the down carbons of the cyclohexane molecule are resting on the surface of the table, whereas the up carbons are floating above them in the air. Contrary to what we may think when we view molecules on paper, the individual atoms in molecules are not static. They can move around. When we have a cyclohexane, this is very obvious when we talk about the ring flip. First, we're going to look at it in a simplified view, talking about the chair versus the high energy transition state, the boat, which represents an intermediary between one form of the chair and another form of the chair. In order to understand how a ring flip actually works, I'm going to take you through a series of steps that take you from one form of the chair through that high energy boat form all the way through to the other form of the chair. Now note that drawing a chair and drawing its ring flipped version is actually quite simple. You just draw its mirror image. This, however, is going to help you understand how we get from that very first structure to that very last structure. The first thing that we're going to do is we're going to look at the original chair and we're going to number the carbons on it, starting with a 1 in the bottom left. Now, I want to point out that this 1 in the bottom left is completely arbitrary and is not me following any conventions. I'm just calling it number 1 because it's going to make this a lot simpler to explain how this works. Again, it has nothing to do with naming or actual conventions in chemistry. So I'm going to start with the 1 in the bottom left, and then I'm simply going to go around clockwise until I have all 6 of the carbons labeled. Next, I'm going to flip the 1 carbon up. So I'm going to show an arrow putting this 1 carbon up into that position right there. This is going to allow me to draw the molecule in that middle boat form. Now, just to show you where my carbons are, I'm going to renumber the carbons in the boat form. So you can see now that the 1 carbon is now way up here because that's where the arrow said we were moving it. And everything else is still connected in the same way clockwise. So that puts our 2 over here, our 3 here, and then our 4, our 5, and our 6. Next, we're simply going to take our 4 and flip that carbon down. So the 4 carbon is going down to this position. Once we do that, we can draw that flipped chair as the mirror image of the original chair. And when we go and number this, we can now see that the 1 is going to be in the top left, and then we're simply going to go around clockwise to finish numbering the molecule. And there you have it. Hopefully with that demonstration, you understand how a ring flip works. Now, it is possible that you are taking a class where the professor cares a lot more about the ring flip than some other professors, in which case I've given you a much more expanded view of the ring flip. This shows an energy diagram of the different transition states and conformations that the chair can take on, and it shows the relative energy difference in these different positions. I'm not going to go over everything in detail, so if you want to study this or understand it, feel free to pause the video and read the text at the bottom. A discussion of the chair would not be complete without talking about axial versus equatorial substituents. Again, usually we start by talking about the hydrogens that are bonded to each of the carbons, but for visual purposes, I prefer, again, to use methyl groups. So first, we're going to talk about axial. Axial means that the substituent is going straight up or straight down. Up carbons have axial groups going up. Down carbons have axial groups going down. So feel free to look at those 2 versions of the molecule, and you can see what I mean when I say up carbons have axial up and down carbons have axial down. Next, we have equatorial, and equatorial means angled up or angled down. Up carbons have equatorial groups pointing down, and down carbons have equatorial groups pointing up. So it's the opposite for the axial and the equatorial orientations. You can see next to that text all of the equatorial positions filled in. One thing that I want to point out here is that when drawing equatorial groups on the middle carbons, the bonds should be drawn at a similar angle to the bonds connecting the outside carbons. By that, I mean, if you look at these middle carbons here and here, you can see that I have the equatorial groups kind of angled up and to the right. This follows that angle of the very outside carbons. On the ring flip version, you can see the same thing. These middle 2 carbons, I have these bonds oriented up and to the left, just like the outer carbons. Just like with your basic cyclohexane, a ring flip can occur in a substituted cyclohexane. What's the most important thing to learn here is that in a ring flip, up substituents stay up and down substituents stay down. However, their axial and their equatorial orientations change. So if we look at the substituted cyclohexane on the page here, you can see what happens when I do the ring flip. On the original version, you can see that I had an up equatorial methyl, and then clockwise to that, I had a down equatorial methyl. When we do the ring flip and move all the carbons essentially 1 position over clockwise, you can see I still have an up methyl group and a down methyl group. However, they're now no longer equatorial, rather, they're axial. To draw a ring flip with substituents is very straightforward. First, you're going to draw a mirror image of the chair without drawing in any of its substituents. Next, you're going to draw each substituent 1 position clockwise of where it was located in the original image. Technically, it's the same carbon due to the ring flip. What you're going to do is you're going to make sure that you keep the direction the same, and by direction I mean up or down, but you're also going to switch its orientation, which again is axial or equatorial. This ensures that if you are on an up carbon, you're going axial up. And if you're on a down carbon, you're going axial down. And following similar logic, your equatorial positions are going to be correct as well. Now, I do want to point out that it doesn't actually matter if you draw the substituents one position clockwise from the original or one position counterclockwise. Both versions would be correct and would actually represent the same exact conformer. Last but not least, we have to discuss how to convert a flat version of a cyclohexane with substituents to a chair version of the cyclohexane. So you can see here that I have a cyclohexane that is substituted 4 times. I have a methyl group and an ethyl group, both on a wedge, and then I have a methyl and an ethyl group, both on a dash. Let's see what this looks like in its chair form. Anytime you have a wedge on a flat cyclohexane, that is going to translate to an up substituent. A dash on a flat cyclohexane translates to a down substituent. To show you more clearly how this works, I'm going to number the carbons in the cyclohexane 1 through 6. This is going to be arbitrary. I'm not doing this for naming purposes. Again, I'm just doing it to show you the relative positions of the substituents. You can see now that at position 1, I have a wedge methyl group. Again, wedge on the flat version translates to an up substituent. That's why I have an up methyl group at the 1 position on the chair. At the 2 position, you can see I have another wedge. This is an ethyl group. Wedge means up, so at the 2 on the chair, I have an ethyl group going up. At the 4, I have a dash ethyl group. So on the 4 on the chair, you can see that I have an ethyl group going down. Likewise, at the 5 on the flat version, I have a dash methyl group. So at the 5 on the chair, I have a down methyl group. Of course, our representation of the chair would not be complete if we didn't show the ring flip. First, I numbered the ring flipped version of the chair. Now, let's compare the flat cyclohexane to that ring flipped version. Again, a wedge means up, and a dash means down when converting between the flat and the chair. So you can see, again, at the 1 and the 2, I have wedges. And at the 1 and the 2 on the chair, I have up groups. Likewise, at the 4 and the 5, I have dashes. So again, on the chair, that ring flip version at the 4 and the 5, I still have down substituents. Now we can also compare the 2 chairs to show that we did in fact follow the rules for the ring flipping. We have the mirror image, we rotated all the carbons 1 over clockwise, and anything that was up is still up, anything that was down is still down, and only axial and equatorial changed. When converting from the flat to the chair representations, there is one thing that I really have to emphasize because I see this mistake made all the time by students. And that is that wedges and dashes have absolutely nothing to do with whether a substituent is axial or equatorial on the chair. This is because that axial and equatorial can change upon a ring flip, while up and down always remain the same. Again, a wedge on the flat does not mean axial, it does not mean equatorial. It can literally mean either one, because if you do a ring flip, it's just going to switch. So again, wedge means up, dash means down, has nothing to do with axial or equatorial. Anytime we have a substituent on a flat version of a cyclohexane, we can redraw that into its chair form and do a ring flip. So in other words, we can represent it with 2 different chairs. Here I have 1s, 2s, 1 ethyl, 2 isopropyl, 1 methyl cyclohexane, and I'm showing it depicted above in its flat form and in its 2 chair conformations. I have to note here that these 2 chair conformations are not equal in energy. When a substituent is equatorial rather than axial, steric strain from something that is called 1,3 diaxial interactions is minimized. If there are multiple substituents, maximizing the number of substituents in the equatorial position is energetically more favorable. If two chair forms both have an equal number of axial and equatorial substituents, the most stable form will place the largest group in the equatorial position. So when we're comparing these two chair forms for this molecule here, we can say that the conformation on the right is the most stable because it has two equatorial substituents rather than one. Not only that, but it also places the largest group, which is that isopropyl group, in the equatorial position, further contributing to its relative stability. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.